Yep, cool. All right, thank you everyone for coming out. I'm Ryan Knight. I run a company called Grand Cloud. I do consulting. I spent a lot of time on like the application development side, doing like Scala, Java development. I also spent some time at DataStax doing Cassandra, Cassandra sales engineer. Actually, before that, I even worked at Oracle. Spent some time at Oracle with the Oracle database and Oracle RAC, way back when. So what I'm going to talk about today is Return of the Transaction King. Does anyone have a clicker? I forgot my clicker, but oh well. I'll just stand behind my stand. It's kind of a pain. All right, so brief history of data. Right in the very beginning of databases, we had relational databases with asset transactions. Right, atomic, consistent, isolated, durable. And this is how databases were for 20 plus years. Asset transactions were really nice and made it really simple to write your applications. If we went back to the LAMP stack days, it was actually pretty simple to write a LAMP application with it because you had the transaction consistency. It made a lot of things really nice and simple. What happened is the internet, right? Traditional asset transactions just didn't scale with the internet, right? People tried all sorts of workarounds with like leaders, with read replicas, distributed locks. Two-phase commits across distributed systems just fundamentally breaks. Right, you would lead it with a read replica, you were left with a single point of failure. Things fall apart when your leader goes down. In the read replicas, you're always having problems with the read replicas, inconsistency in the read replicas. So traditional asset transactions really just didn't work in the internet era. They really fell apart. And this led to the CAP Theorem. Probably everyone here has heard of the CAP Theorem. This trade-off between consistency, availability, and partition tolerance. And what this really means is that for a long time, people talked about, where in the CAP theorem do I lie? To get true consistency, I had to trade off availability, or vice versa. So what companies were really left with was this trade-off between, do I want global scale or do I want strong consistency? And which one do I choose to build my applications on? And a lot of companies chose global scale. And this led to the rise of eventual consistency. So eventual consistency has really become the predominant model today in most applications. And eventual consistency is done at the sacrifice of strong consistency. So there's been this trade-off for a long time. So if we look at eventual consistency is really just a necessary evil. Right, eventual consistency is not something any of us really want to deal with. And so, we've invented all sorts of workarounds to deal with this eventual consistency. Like last write wins. We have, event sourcing models. It's all these different models that basically we write the data now and we'll figure out later and how to sort it out later. That's what event sourcing is a lot about is, I write my series of events and I do roll up and snapshots. And so I figure out how that data, is what the value, like if I'm doing bank transactions, I figure out what the value of my bank account is after the fact, after I can add all those transactions together, the bank account transactions together. So this is really the eventual consistency model, and it really works really well, right? Event sourcing works really well. It's a very predominant model in the industry today, and it's used across the internet very successfully. Right, so DNS uses it quite extensively. IoT, like any time series use case, monitoring web metrics, followers. Right, if I'm taking a count of metrics of how many people hit my web page, that can be eventually consistent. Right, I can if I add when I do an additive of all the metrics of a web page hits, that can be associative, and I can add that in different orders, and you always get to the same answer. There's also been a lot of use cases where people figure out how to modify the business to allow for inconsistency. It's very common for online stores to oversell, right? They figure that they have about 1,000 items and they'll sell 1,000 items, and then they'll they might sell 1,002 and only have 1,000 items and just say, sorry, we don't have your item in stock, reorder. Or, right, the bank has an overdraft charge, right? So there's a lot of ways of modeling your business to fit in with this eventual consistency and event sourcing kind of models that work really well. But where it falls apart, and I was talking to James Ward about this, the thing is we live in a stateful and finite world. So there's oftentimes these cases, because we're in a very stateful and finite world, we don't have the ability to just say, well, maybe we have 100, maybe we have 102, it doesn't matter. There's a lot of use cases where we have a finite number of things we need to sell. And so what that leads to is there's places where event sourcing breaks down. Right? There's a lot of use cases where the order of events matters, where I have to have an exact linear order or serializable order of events. And when this exact order of events matters, what happens is if I have two hosts or like two servers who are writing my events in parallel to my database or my any kind of data store, these events can get out of order. When I can't guarantee that these events that are being written in parallel are being placed in the exact same order, I'm going to end up with a divergent history of events. And so then I end up with the problem of how do I reconcile this divergent history of events. And I also end up with this problem of the possibility of losing some of my history of events. So there is a slight problem that if I'm writing from multiple servers the same events, that there's cases where I can actually lose some of my history. Right? So in these use cases where there's really the ordering really matters, this is the places where event sourcing starts to break down. A common example that I can talk about is like a reward system. If I have to process a batch of rewards, as that rewards comes in, you can imagine the batch of rewards that I'm processing from, say, like a single user does, like accrues points, and then redeems them. Well, what if that's the history I saw the first time through, is I'm redeeming those points? Well, what if the actual history was accrue, void, and then redeem, and I missed that void? Right? And because I'm processing these as a batch of transactions, I might not receive that void until after the redeem. And so there is a very specific use cases where that ordering of events for something like redeeming points matters. Another problem is like dealing with a void. What if the order of those transactions comes in as a void then a redeem? So they're coming in out of order, and I've got to deal with the void, but I don't have the redeem. So these kinds of situations really matter. Another example is like an auction. If I'm auctioning a particular item off, I want to know the exact order the bids on that item were received, and I need to know the exact ordering of those events. So there's these times where event sourcing really starts to break down. So a lot of people talk about strong consistency, and there's a lot of different definitions of strong consistency today. When I talk about strong consistency, this is actually from the Google Docs about one of their databases. They talk about how they see strong consistency. And what they define as strong consistency is that I have server A is writing value X to node A, right? Well, when I read from node B, it's going to block for the reading of X, right? So it cannot read X while it's being written to, right? And at the same time, node C is also going to block for reading of X. So what's happening is the readers are blocked until the replication is complete. So when I talk about strong consistency, there's a lot of different definitions. When I'm talking about the ability to have it written to node A, and then node B and C are not going to be able to read that value back out until it's completed. So this is a much stronger sense of consistency than other definitions. Right, so in the industry, we see a lot of different views of strong consistency and how people define consistency. Oftentimes, people will call strong consistency if I write and then I read from the local quorum. They call that strong consistency. So there's different opinions of how consistency is defined. What I'm really talking about when I talk about strong consistency is the ability to do a read before a write. So I want to read a value out of the database, update it, and then write it back down. Right? So things like compare and swaps, also getting like snapshot isolation. So this is a much higher level than just a strong consistency of a write and then read and to get the same value back out. So this is a much stronger guarantee that I'm going to actually see an updated value that I read back out of the database. So when we talk about strong consistency, one of the things we're talking about dealing with is the ability to avoid what's called write skew. So write skew is, right, I have two concurrent transactions, each determine what they are writing based on reading a data set which overlaps with what the other one is writing. So you basically have two people trying to read the same set of data and update it, but then they're overriding each other, and so they write the wrong values. So you get a skew in your write values. So this is one example of where you can get like a skew of data, or basically your data gets out of alignment. So can we really ignore consistency? Can we just say, all use cases are eventually consistent and we'll sort it all out later? I think when we do that, we're really pushing the consistency problem into the application where the problems are much harder to solve. So by saying that everything is going to be eventually consistent, we're really saying that we're really not avoiding the problem. We're just saying that we're going to be eventually consistent at the data tier. And what we really need to think about is, well, are we really modeling things eventually consistent throughout the entire layer, or are we really just pushing consistency up into the application tier and dealing with there? And when we do that and we start trying to model the consistency in the application tier, we get into a lot of complexity. So there's a lot of ways to deal with this complexity in the application tier, but it puts a lot of burden on the application developers to have to deal with this. So some of the common patterns of consistency in the application tier that I've seen is event sourcing with command serialization. Right? So when I write that command for my event, I do all the, like I serialize on a particular command. So like I might have a user ID, and all the commands for that user ID, I'll go through a single like actor. So some kind of a serialization point, so I can guarantee that when I'm writing all the events for that particular user, all the events are being written from a single server. Or you can do a serialization point like a Kafka consumer. So I can say, this Kafka consumer is dealing with this specific topic, and I'm dividing my data out such that I can guarantee that the ordering of events that I'm processing are going to be in exact linear order. Well, this works OK until things start to fail. So what happens if I have a single command writer for a single user, and I can scale that across like an Akka cluster and have Akka actors dealing with those commands and guaranteeing that I'm getting those orders right. But then if a actor or a node in my cluster goes down, I then have to deal with write timeouts. So how long do I wait for that database write to time out before I know that I'm going to have to fail over to another node? So, and then at that point in time, I'm starting to have to deal with a lot of failure cases of what happens when things are going to break. So this gets even worse with the rise of cloud-native microservices. So with the microservice architecture, I should say, monolithic, it's pretty easy to deal with event sourcing and guaranteeing the ordering of events. When I get into a cloud-native like microservices type of architectures, things really increase in complexity. So one of the things is the partition of the application domain and the related data. So how do I figure out which services are dealing with which data, who's dealing with the events, who's writing these events? And I'm having to deal with a lot of increased coordination between these datas. So if I have different services who are having to coordinate on a particular event or having to, one reads and one writes, how do I do the coordination between these? So all these kinds of things, as things scale up with microservices, you get a scale of an increasing exponential growth in complexity, which makes things a lot harder to deal with. So I really think that when you look at a cloud-native architecture, you add NoSQL databases, and you completely take out an ACID transaction, you end up with almost this Rube Goldberg machine of data, right? So you're trying to figure out between these hundreds of servers, how do I coordinate all the data between all these services? So I think this leads to a lot of complexity when you're not having this very strong sense of consistency between my application and my application tier. So let's just talk a bit about when we say ACID transactions, why would an ACID transaction be important? So atomic is guaranteeing that I have my operation is actually an atomic operation. So if I do multiple read writes or writes reads, those all happen at in a very atomic level. It's an atomic lock that I'm guaranteeing that that's a single unit of work that's being done. Consistency, not only a strong consistency, but also that it's correct. So am I affecting other pieces of data that I shouldn't be? Isolated, is that transaction being isolated from the other effects that are happening in the database? Is it durable? Is that transaction actually committed before someone else tries to read it? So it's a much stronger sense of dealing with my data than just a strong consistency. So it's really taking this to a much stronger level of guaranteeing what's happening to my data. So what I really think is that when I talk about return of the transaction king, what I really think is that I think we're seeing a return in this industry of ACID transactions combined with event sourcing is where this industry is headed. So I still think the event sourcing model is a great model. I think there's probably 80–90% of the use cases in businesses today really work well for event sourcing. And I think a lot of any kind of NoSQL database that does event sourcing is a phenomenal database for those exact reasons. So I think there's still a really strong use case for event sourcing, and I think there's just this is more kind of I see this as figuring out which use case to use which database, and where these different models of architectures fit in. So I think the problem that we've run into as an industry is we're trying to make everything fit into an event sourcing eventual consistency, where it can't. It just fundamentally can't, where I think there are use cases where we actually need ACID transactions. So when I talk about the rise of transactions, there's a couple of databases out there that are really adding in this strong consistency back into the core of the database. So these are databases that have both global scale and strong consistency. The three primary ones that I know about today are Fana, Google Spanner, and Cockroach DB. And these are really kind of next generation databases I think are going to fundamentally change the way we can program our applications because we get a return of transactions. One second. How many people here have heard of these databases? Has anyone heard of Fana? A couple people heard of Fana. Spanner? Anyone heard of Spanner? Cool. How about Cockroach? You guys have heard of, so you guys have heard of a lot of these? Cool. Is anyone using any of these databases currently? No one yet? Okay. So what is the value of transactions? Why would we want to add transactions back into our application layer? I think by adding in transactions for these use cases where I need true strong consistency at the highest level, where I truly need an ACID transaction, I think it really decreases the complexity in your application tier. It reduces the cognitive overhead of complexity of trying to figure out, how do I serialize these, writes? How do I figure out, who is reading and who's writing the data at what time and what point? If I can serialize that all by having a transaction, it really makes the application tier easier. I've seen people go as crazy as writing their own Paxos algorithm to deal with eventual consistency in the application tier. That's a really hard thing to maintain at a business layer, at an application tier for your business logic. I think by returning to transactions and using them in the right use case, you really can increase your developer productivity, and you also can focus more on your business value. Right? Oftentimes I'll see developers who are trying to focus on, they spend so much time dealing with eventual consistency and event sourcing in the application tier and trying to work around all the problems that causes. They're not really delivering business value. They're more trying to build their own, like Paxos consensus algorithm, or some kind of, complex, data management layer at the application tier. And I don't think that's where it really fits in. So I think this is a huge boost both for developer productivity and for businesses. So there's always this interesting discussion around, do we have to sacrifice availability and partition tolerance to get consistency? There's a lot of debate about this. I'm not going to wade into this fully. If you're really interested in there's two papers you really need to read. Eric Brewer in the Spanner paper, where he introduces Spanner, he talks about, he says there's two important caveats to his, Eric Brewer is the inventor of the CAP theorem. He says there's caveats in my theorem. He says, first, you only need forfeit something during an actual partition, and even then there are many mitigations. Second, the actual theorem is only about 100% availability, while the interesting discussion is about the trade-offs involved for realistic high availability. So what he's really saying is, do we really have to sacrifice everything? Do we have to sacrifice consistency because of AP? There's another really interesting paper about this by, I'm not quite sure how to say his name, Daniel Abadi. He talks about the problems with the CAP theorem and Yahoo's low known NoSQL system. And what he talks about is, under normal conditions, do we want to really, what we really should be thinking about is the trade-off between latency and consistency. And he goes into this in a lot in depth about why he thinks that the CAP theorem is overrated, and that we really should start thinking about, under normal conditions, we should be thinking about the consistency and how, this trade-off between consistency and latency. So if you look at Google and that Spanner paper, Google actually talks about their modern chubby cells. That's their compute units. They have over 5 nines of availability. Their availability at this point in time is so high that they're saying, you know what, we have so little outage that let's start focusing more on consistency. And that's exactly what they built with Spanner. So just a really brief introduction to Spanner. I think Spanner is an absolutely fascinating database. The way they've actually built Spanner is Google has its own private network around the globe. So they actually have laid, all of their data centers are interconnected by their own private network across the globe, which guarantees very high bandwidth. They also have in each data center GPS receivers with atomic clocks. So they have this guarantee of being able to know the exact time at every single data center around the world at any given moment. This is something that's really unique to Google and no one else has. And by having this exact time, they can provide serializability guarantees that no other database can provide. And so this is the way they built Spanner, is built on top of this concept of these serializability guarantees. And so, it's interesting. I've talked to I have some friends that work for Google, and we talked a lot about databases and the trade-offs between different database approaches. One interesting thing I found from Google is their core business is ads, and their core business of AdWords has never moved off of a relational or off of a transactional database. So they were originally built on top of MySQL. They sharded MySQL. They were actually running off of MySQL for a very long time, and they kept the AdWords on a transactional database until they could invent their own, and they built Spanner. And actually, AdWords has been running on an internal version of Spanner for over 5 years. So for them, the AdWords platform is such a key part of their business, where they're dealing with people's, they talk about dealing with people's money and financial transactions. What they say is, when we're dealing with people's money and we're dealing with financial transactions, we don't want eventual consistency. We don't want the question of whether or not I've been able to sell that ad. I don't want to have a question of, am I going to be able to, earn the revenue I need to? And for this reason, they've kept Spanner on a strongly consistent asset transaction database for their entire history. And what they've done is they've basically taken Spanner, they're now making this a commercial product on the Google Cloud. One other use case of Spanner is the Google Cloud Platform. Actually runs, the whole control plane is backed by Spanner, by a strongly consistent asset transaction database. One other interesting thing they do is they actually separate out compute and data layers. So they can actually take their data and just plug it into another compute instance. And so that allows them to have no scheduled downtime. So if they need to upgrade a compute instance or a server for any kind of reason, they can actually just plug your data into another compute instance. And that allows them to do maintenance by just moving your data between nodes. Cockroach GB, it has hybrid logical clocks similar to a vector clock for ordering your transactions. They deal with a lot of challenges with clock skew. They can wait up to 250 milliseconds on reads. I'm still, in my mind, I have a lot of questions about whether or not they're really going to be able to pull this off. I mean, they're basically trying to do their own version of Spanner without the atomic clocks, which is really a challenging problem. So the one database that I've been spending a lot of time on evaluating is Fana. And I think Fana is a really interesting database because it has the global transactions. It has the global scale plus the strong consistency. So you have global transactions around the world without depending on atomic clocks. So they have an entirely new approach to how they deal with transactions in databases. And this all comes out of the spelling error in my slides there. Sorry. So the people who founded Fauna came from Twitter. They built a lot of similar systems internally to Twitter. They dealt with massive scale at Twitter, and solving all the reliability and the fail whale problems at Twitter for a number of years. And based on that experience in building massively distributed systems, they took that experience. There's also a very groundbreaking paper called the Calvin paper that was written that talks about a new approach to writing databases. And they took these two things and they built a new generation of database. The other unique thing I think with Fana is that Fana is it's a functional type safe, right? The query language is a functional query language. So it doesn't use a normal SQL approach. So what they've done is, most databases like Spanner, they try to, be SQL compatible. Fana said, well, what's more important is if we're going to build a modern database, let's build a modern language to use with our database. It also has indexes. So I can do multiple indexes, any kind of indexes across my data. I can do constraints. I can do views, all these kinds of things. So how does the transaction resolution work? What it really does is it resolves these transactions before committing them to the database. So what it has is it has this RAF replicated log of transactions. This derives the total ordering of transactions. And so when I write a transaction to the database, what it does is it puts it into this like epoch batch, and it does a global resolution of that transactional log. So that's a very high level skimming over it. So they do a lot of things to avoid cross-regional replication. If that batch of functions only has a read, then I can do optimistic locking. All these kinds of things to optimize this entire process. But the novelty is the fact that instead of trying to do a lock on my database, right? So a traditional ACID transaction is like begin lock, do a select, insert an update, and then unlock. Instead, what they're doing is they allow you to take a function and send that function down to the database. That function is the unit of transaction, and it takes all the functions for the epoch, and it resolves them together, and then it applies those to the database. So this is really a novel approach to how you build your database from the ground up. I talked about most of this, yeah. Let's see here. There's a lot of other unique features to Fana. It has native security and access control built into it. So every query that you make actually has to have an access key. And based on that access key, I can determine at the row level whether or not I am allowed to access that data. This provides complete data isolation across data sets. The other interesting thing is that key that I'm accessing the data with, is that key or that token, is also used for scheduling the priorities of that query that I'm running. And so what they do internally is they actually have more of like an operating system-like design. And what this allows you to do is a single cluster for different and competing workloads, so that I can have, in a single cluster, I could have an analytics cluster along with my traditional OLTP cluster, and I can give different priorities to different queries. And I can also assign different priorities to different users. So I'm combining these very tight security controls with the quality of service controls, which allows me to use that database for a lot of different purposes without affecting other people. Another interesting thing is temporality. Fana keeps all instances of its data. Right? It doesn't ever override them, but it just creates new records every time it writes. The data representation in Fana. So this is the other unique thing about Fana, is you have your database. Your database has what they call classes, and then I create an instance of that class, and that instance has array or scalar types. But I can also do nested data. So within a single database, I can have multiple databases, and inside of a database, I can have multiple classes. So I can have nested objects, and this allows me to have relationships in my data. Instances. Records are stored in the database as an instance. Right? All objects are instances of a specific class. So the core row-like concept or like a partition in Fana is a class. So I create an instance of a class, and I store that class gets stored in a database, and I get a ref back from that class. And so that reference refers to that unique instance of that class. So the transactional scope is a functional transactional scope. So the entire function or query block is the scope of my transaction. This is a paradigm that's going to feel very natural to functional programmers, because the way you work with Fana is in a very functional kind of a manner. So I think for anyone with a Scala background who's used to doing functional programming is going to find this a much more intuitive model to work with Fana. And then it has indexes similar to a traditional database. The unique thing is the indexes you index on a particular term. I say I want to give an index of this term, and these are the values I want to return. So you specify in your index what values are going to be returned from the reading of that index. And that index is also what's used to enforce the uniqueness constraints on the database. And then the query optimizer does not make the index, doesn't choose for you which index is being used. You have to specifically reference which index is being used. All right. I'm going to show a little bit of code. So let's see here. So this is, I was working on a little sample that is kind of like a contract between two users. So the idea is that, right, I have let's see here, let's scroll up here. So I have a creditor and a debtor. So I want to make a contract where one person lends another person an amount of money, and I want to know the state of that contract, whether it's proposed. Have I proposed lending you money? Have I accepted, redeemed, or rejected that contract? So to look at a little bit of the Fana code of how I write this. So with Scala, and they have a new driver out that has a codex that automatically serializes and deserializes from case classes. So this will allow me to automatically write that user class. Let me break this down for you a little bit. So I talked about how the fundamental unit in Fana is a class. So when I set up my schema, the first thing I do is I create a class. So here I'm saying, create class. The name of that class is user. And then I'm going to do a query to check to see if that user already exists. And then I want to create an index on that user. So I want to do an index by username. So this is the name of my index, the source of the index. So I'm saying the source comes from this particular class. And then the terms of this index. So this is what I'm going to actually index on. These are the values I'm indexing on. So I'm just going to index on the username. So when we talk about a functional scope, when I actually run this query, so here's where I run the query is I do this if. So I'm doing a Fana if query. I'm saying if this class does not exist, then create it. Otherwise, just get it. So here I'm passing in a functional scope to that. And then similarly, we have a contract. A lot of the same concepts here, right? So let's scroll down. So here I create a class called contract. My contract is going to be between two parties, right? And then I'm going to create an index on that contract where I have a contract by ID. And the terms I'm going to index on are on that contract ID. So now that I've created the class, I'll show you a little bit about how we can actually use that. So everything is done with this client is defined. I'll back up just a little bit. I basically have a Fana client, which is my connection into my database. With that client, I'm saying let's create a user. So what I'm saying is I'm creating a user in the class user. So I'm saying what user, and then I'm specifying the data for that user. All right, so the data of this instance is a user ID and a username. So that's going to create a user. And then going to how it's a functional language. So as an example, say like I have a list of 5 users. So this entire block is a single Fana query or function that gets submitted to the database. And I've submitted this query to the database. I'm basically passing to the database 5 users. And I'm going to iterate over each of those 5 users. I'm going to say for each of these users, do this function. And I'm going to do a lambda. I'm going to map over those users. And I'm going to create an instance of those. What's unique about this is this is not 5 separate queries that are being issued to the database. This entire block of code is being issued to the database, and that function is being run inside of the database and mapping over those users. So in a similar way, I can get the data back out. So here's an example of using that index. I index by user by the user table by username. So if I want to read a user out of the database, for example, if I want to find the user Hydro, so what I'm saying here is I want to get something out of the database, and I want to match on the index. So the index I want to use is the user by username, and the value I want to match is Hydro. So I'm basically getting the ref back out of that data. So here I'm saying basically select. By default, what I'm getting back is just a reference to that object. So I don't get back the actual data. I'm just getting back a ref. And so now that I have that ref, so I basically have a pointer to that class. Now that I have that pointer, I want to get the actual data out of there. And so what I do is I say get a ref. So that's actually pulling that ref out of the database and giving me the actual values out. So the first step is just to select the ref and find it, and then I take that ref and I pull it back out. But again, this is all done inside of the database, so this isn't a two-step process, back and forth the database. This is all done in a single step. So a little bit more of a complex example is, say like I want to, let's see here, test, I want to go to contract. I want to create a contract, right? A contract is between two users. So to create the contract between two users, I first need to look up those users. So if I get something from the, if I get a request from the client saying I want to match user Hydro and user Bob and create a contract between them. So instead of having to go to the database and looking up user Bob, then looking up user admin, and then getting those values back, and then creating a contract and then storing that back in the database, I can do this all in one functional chunk. So what this query does is, right, I'm creating a query. Inside that query, I'm going to create a class of type contract. And the value, so like the value of creditor is going to be based on a select. The value of debtor is going to be based on a select. So I'm basically, inside of that single functional block, I'm looking up the creditor, I'm looking up the debtor, and I'm saying those values inside the contract. Those are returning the ref. So then in terms of redeeming the contract, again, this is going back. So this is really where we get into this transactional type of approach to our database. So here I'm saying, let me highlight this. So this is, if we look at this section of code right here, what I'm saying is I want to look up a contract by ID. So this is, let me back up. This is saying I want to redeem a contract. So like I have a contract between two users. I now want to redeem that contract. Say, is this value, right, has this contract already been redeemed, or can I redeem it? So I wanted to have the strong sense of guarantee of whether or not this contract has already been redeemed. Right? So if I'm dealing with money and I say, well, Bob owes me $5, I want to know for sure whether or not that he's already paid me or not. So the way I can do this in Fana as a functional transaction is I can say, go and look up the contract. Right? So I'm matching on that index contract by ID. I'm getting back the contract reference. And then I get the state of the contract. So is that the state of that contract? Is it just in a proposed state? Have we just started the contract, or have I already redeemed it? So I look at the state of the contract, and I say, right, if equals state redeemed. So if I've already redeemed that contract, that function will error out, and it's going to return an error, already redeemed. Otherwise, I'm going to update the contract, and I'm going to set the state to be redeemed. So this gives me a functional scope for doing my transaction. Inside this functional scope, I'm able to do basically an asset transaction of reading the values out of my database, verifying what they are, and then deciding whether or not doing something based on that value. As a more complete example, so obviously there's a lot of ways to break this down. So this is like a bank account transfer between two customers. So here, what I'm doing is I look up the source balance between a source customer and a destination customer, right? And then I'm comparing, and I'm basically doing a calculation of their. What I'm doing is I say, right, I want to look at your source balance, and once I take out your source balance minus your value, are you going to still have enough money, to make this transfer? So I'm saying, is the value going to drop below 0 so I can't approve this transfer, or is this going to be allowed? Right, so I basically get the source balance, the destination balance, and I do some math to see if this is going to be, the math works out. And what I can do inside of this functional scope of the database is I'm actually doing the subtract, I'm doing the add, and then I'm saying an if statement, right? So if my source balance is greater than 0, then do this query. And inside of this query scope, I want to do a number of things. I want to create a transaction. Right? So I want to keep a transaction log. I'm still doing event sourcing. I'm still keeping a record of all the events that have happened. So I know exactly what transfers happened and who, what money went from who to who. But I'm also, at the same time of keeping this event log, I'm keeping an exact account balance. Right? So I'm updating the data for that customer, for the source customer, the destination customer, and giving them an exact balance so they know that their account, when they look at the amount of money they have in the account, they know that it's exact. So cool. Am I out of time? Yep, cool. All right, I'll be around after the talk if you have any questions. I'd be happy to talk to you guys. So cool. Thank you, everyone.